And now I want to use characteristic classes as an application in essentially a subject called group cohomology. So let's recall, so what we have is that, so BG is the classifying space for principal G bundles. This is very general, and at the end of the lecture, I'm going to kind of just recount some of the basic yoga here for thinking about the significance of BG and both sort of more homotopical and the more geometric approaches to the subject. But if G is finite, then this is a space so that whose homology ends up being something called the Tor groups over the group ring of G. So that's just this associative but not commutative algebra of K with itself, if K is our coefficients, and I guess I'll put a K here as well. So I'm thinking of K like Z mod P or something like that. And that's because you can check that the cellular chains of this particular B delta G form a resolution, and well, of E delta G form a resolution. B delta G, you get that tensor product that defines this Tor, and so the homology of this is the same as this Tor group. And similarly, the cohomology of BG has a purely, and the point is, this is purely algebraic. You can define these, again, just through resolutions. Take KG, that only depends on the group G. No topology around. Take K as a trivial module over KG and start resolving it. And you find that these are useful in algebra, and you also then have the space around whose cohomology is that algebra. A key example, basic in so many ways, is G is the cyclic group of order 2. That's also a symmetric group on 2 elements. That's also the orthogonal group in 1 dimension, just multiplication by plus or minus 1. And we really find that, that if we think about, say, twofold covers, there's a one correspondence between those and line bundles. This direction here, given a line bundle, I can take the sphere bundle. The other direction is a little more complicated, but you can just take a formal span and then just sort of set x to minus x that you're, or x. Anyways, you can take the 2 points in your cover and treat one as 1 and one as minus 1 in your rank 1 vector space. And all of these then is, so for all of these, BG is RP infinity, and so the group cohomology is, we're just going to think about the prime 2 as just a polynomial ring, and that's just this example that underlies a lot. But now let's apply some of these. This will be another one of our applications of characteristic classes to group cohomology. So I want to understand, so I'm going to study the BSN, and what this I can do is, if I look at configurations of endpoints in RD, it fibers over configurations of n-1 points in RD, and the fiber is a wedge of d-1 spheres. as D gets large, that's contractible. So if I let D go to infinity, then this is an ESN. And so then, so the quotient, which is basically unordered configurations, is a model for the classifying space of the configurations, and we'll come back to that. And so let's give a concrete example. Let's consider BS4. And define a bundle over it. Through the regular representation, through really thinking of Sn through permutation matrices. That is, I've got some basis vectors E1, E2, E3, E4, and they are permuted by S4. So that defines a representation of S4, of course. And then we can, let's just call it, well, let's see. So, sorry, we wanted to define a bundle over it through first defining representation. S4 acting on some V is going to be the span of E1 through E4. And then we're going to just let S4 act by permuting the indices. And then take V crossover S4 ES4 is a bundle over BS4 with fiber rank 4. Okay, so that's a vector bundle, and I want to compute its Stiefel-Whitney classes. Well, you would say, all right, well, first of all, what's the cohomology of S4? And I would tell you, well, S4 is not so bad, but this is actually a little backwards. This is a characteristic class calculation that comes in the process of computing the cohomology of BS4, generally BS2 to the n. So what do I mean by compute its Stiefel-Whitney classes? Well, of a pullback. So in other words, if I've got some vector bundle over a space, I don't understand the cohomology of that space, I could at least pull back the vector bundle somewhere whose cohomology I do understand and maybe compute there. And this could actually give us some information about the cohomology of the original space. So what I'm going to do is note that this rank 2 vector space over F2, which is, of course, just the Klein-4 group, it acts on itself by multiplication, right? And it implies that we get an embedded a subgroup of S4, which I'm going to call it V2. And it's the subgroup which has the identity element, the permutation which swaps 1, 2 while swapping 3 and 4, and the other conjugates of that. So that's explicitly the subgroup of the symmetric group on 4 letters. And then let's now take, this is our vector bundle E. Now let's pull back E to BV2. So, and analyze the pullback or restriction if we use a model where it's a subspace of E over BS4 to BV2. Okay, so BV2 is a product of RP infinities. So these are going to be some bundle over just a product of two RP infinities. And we've got this permutation presentation of V, and I claim that there is there's a trivial line bundle which is the span of, for those who worked with a regular representation before, you'll recognize this. The four basis vectors are permuted by the action. Therefore, when I look at this quotient, E is defined as a quotient. This sum is going to be fixed, and its span then defines a subbundle of E. And it's a trivial line bundle. That vector doesn't go anywhere, so I can take a section whose values is exactly this E1 plus E2 plus E3 plus E4 over BV2, and a line bundle with a section is trivial. So, but then let's look at, I also get a subbundle which is spanned by so what I mean by this is, this vector and then its opposite under all four of these elements. So for example, if I swap 1 and 2 and swap 3 and 4, let's just call these A, B, and C. So that element A, it fixes this. Whereas B, if I swap E1 and E3, as well as E2 and E4, this vector goes to minus itself. But that's okay in terms of defining a line bundle. If I include just the R span, and then of course I would need to say plus minus. If I include the R span, if the action of B sends this to minus itself, then that is going to be a well-defined subbundle. And see, we have that A acts by 1 on this, and B and C act by multiplication by -1 on this bundle. And then similarly, I have if I look at the span of E1 minus E2 plus E3 minus E4, or the span of E1 minus E2 minus E3 plus E4. All of those are things that each of A, B, and C either fixes or sends it to minus itself. So then that span is a well-defined subbundle when I pull it back to V2. And even though, as I'll make note, E itself over BS4 doesn't split it as a sum of line bundles. What this means, if I look and then see that this then spans all of E pulled back to V, so that means the restriction or pullback of E to BV2 is a sum of line bundles. And what are those? Well, if A acts by 1 and B and C act by -1, then really it's you have to name your copies of RP infinity, but we can just call that a tautological line bundle on one factor of your two factors of RP infinity, or the tautological line bundle on the second factor of RP infinity. So it's trivial on the first. It's that tautological bundle pulled back via the projection from RP infinity across RP infinity to RP infinity. And then the final one, if you have, say, C acting trivially, but A and B acting non-trivially, it's actually isomorphic then to the tensor product. Okay, and so let's remember the cohomology of BV2 is isomorphic to a polynomial algebra on two generators, and so the total Stiefel-Whitney class of the pullback of E is, well, it's going to be the total, the product of the Stiefel-Whitney classes, and it's going to be the trivial line bundle. It's just 1 or 1 plus 0. For gamma 1, that will be 1 plus x1, the generator of the cohomology of the first factor of RP infinity. Gamma 2 is 1 plus x2. And then the tensor product, I'll leave as an exercise. That this this tensor product has total Stiefel-Whitney class 1 plus x2 in degree 1. So in other words, it's first Stiefel-Whitney class of that line bundle, which is an Euler class, is the sum of those two homology classes. And so you can expand this, and so that means the total Stiefel-Whitney class is 1 plus, there's cancellation when you look in the first degree, so that means that W1 is going to be 0. We get x1 squared plus x1 x2 plus x2 squared in degree 2. And then we also get, there's a couple of ways to put it. I'll just write it x1 x2 times x1 plus x2. Or in other words, x1 squared x2 plus x1 x2 squared. So this is my W2, and that's my W3. Notice that these are symmetric polynomials, but they're actually, these expressions are all manifestly invariant under the group under the group GL2F2. It acts on the linear span of x1 and x2, but then it also, that extends to an action of GL2F2 on any polynomials. If I send x1 to x1 plus x2, then I know what to do for a polynomial. These invariants are called Dixon invariants. So what we've proven in this example, and I'll give a general theorem, is that the cohomology of BS 2 to the n, and maybe I'll also leave it as an exercise for you to work this out, at least for n equals 3, it maps to, through this characteristic classes construction, the polynomials and n variables that are GLN F2 invariant. This is what's called the Dixon algebra, because Dixon calculated these almost exactly a century and change ago. That was his thesis. He was probably tenure track at this point. So this is just a sub algebra of all polynomials. But you have this, again, this is some x over the group ring on the 2 to the nth symmetric group with k and k. So somehow related to module extensions and resolutions, there's an interesting homomorphism that's non-trivial, that's surjective, in fact, onto this Dixon algebra, which ends up being a polynomial algebra always, in degrees 2 to the n minus 2 to the l for l less than n, starting with 0. So there's a Dixon generator in degree n minus 1. It's, in this case, it's x1 times x2 times x plus 1 plus x2. There's always, you can play that game. The next one is in rank 3. There's 7 non-zero elements of the F2 vector space spanned by x1, x2, x3. You list them all out, you multiply them, you get a 7th degree polynomial, which is got to be invariant. But then there's also polynomials in degrees 6 and 4 in that case. So another exercise will be to do that algebra. So similar to symmetric polynomials, but much less well known. So that's kind of fun. This is the application. We used vector bundles in order to construct a homomorphism from something algebraic to something else algebraic. If you reflect, this is a cousin of this. This looks very similar to what we did for Grassmannians, which we can rewrite as BON. So in fact, there's a general phenomenon there's a little theorem that if H is a subgroup of G, then when I restrict the cohomology of BG to the cohomology of BH, that really I don't map to the full cohomology of BH. There's an action of the normalizer of H. That action is trivial on H, but anyway, there's an action of the normalizer of H on the cohomology of BH, and this factors through. So this all requires, I'm not going to take the time here, so the proof requires proof uses, as far as I know, the only proof I know uses the simplicial B delta G model for BG in a serious way. And it's a lot of fun. You can see the fifth video in my algebraic topology from a geometric viewpoint series. So look at video 5. Video 4, I think, introduces BG. Video 5 ends with this argument here, which is one of my favorite. It's actually a very kind of geometric argument on this B delta G. And so, again, as much as I love, for example, the configuration space model for classifying spaces of symmetric groups, this speaks to having multiple models. Getting back, though, to, let me say one more thing about the cohomology of symmetric groups. Oh, actually, let me just say that the example, we can reflect on a couple examples that we've already seen. If G is O(n) and H is O1 to the n, then, so matrices with just pluses or plus minus one along the diagonal, then it turns out that the normalizer mod H, that's often called the Weil group, is Sn, and we've already seen that the cohomology of BOn, which is GRN R infinity, when I restrict to the cohomology of O1 to the n, which is a product of RP infinities, then then that restriction we found was Sn, 1 to the Sn invariance. And in fact, it was isomorphic onto the image of the Sn invariance. So this gives a sort of a general phenomenon. It was clear enough that the image should be symmetric polynomials from our definition, because linear dependence was a symmetric condition. But still, this actually puts it in a broader framework. Lets us understand that calculation and this bit of algebra where you have some kind of invariant polynomials in a new light. And the example we just talked about is G is Sn, H is what we're calling Vn. It's isomorphic to C2 to the n as a subgroup of 2 to the n. And then because you can really think of this as, well, F2 to the n, then it turns out that the normalizer is sort of affine linear transformations over F2. Those are the ones that preserve addition. And then if you get rid of the action of F2 to the n on itself, you get exactly GLN F2. So the characteristic classes calculation led us to see some invariant expressions under GLNF2, but in fact, the general theory predicts that we would need to map there. So let me say one other thing before leaving cohomology of symmetric groups. So we showed that we have this homomorphism onto these symmetric polynomials. The other thing I wanted to say is that, so that's one point of, so this bundle construction analysis applies some kind of geometry topology, to the study of group cohomology, which again, I'll just emphasize, I can think of as purely an algebraic question. But there's in fact more geometry to be had. Because, and let's think about, so configurations of endpoints. Let's just go R capital D for sanity. This is similar to Grossmanians of n-planes in R capital D. If I take this bundle, this is a universal SN bundle as D gets large. And I can really think of this as you know, I mean, just explicitly, I've got all labelings of points. And the point is that that I can, before we have both an abstract classifying map for vector bundles and the first geometric classifying map. So, so what we can do is, so for any covering space, if I have some cover of X, which is an n-sheeted cover, then if X is paracompact, I can embed this in X cross R D, and then the fiber over any X is just going to be a configuration, the intersection X tilde intersect that little X cross RD is a configuration of endpoints in RD. So just as we embedded line bundles or more general vector bundles in a trivial vector bundle, we can actually embed covering spaces in a trivial vector bundle. And the point is then that we can use the geometry. And in fact, it's very much like Schubert. So I'm going to call it Schubert-inspired geometry to define the cohomology, define the characteristic classes. And the fun thing is that although cohomology of symmetric groups was been something that starting really back to Steenrod recognized their importance for Steenrod operations. So that was in the early 50s, and Nakooka calculated an additive basis in about 1960. And then various other folks like Cohen-Lada-May sort of gave various bells and whistles, but the ring structure and other things were fairly mysterious. And it turns out that just 10 years ago, some collaborators and I used this Schubert-inspired geometry. We rediscovered a second kind of product structure in the cohomology of symmetric groups. And these characteristic classes for finite sheeted covers were really just first described as such in 2010. So let me, so that's some geometry further geometry that ultimately has to do with this X calculation. So let me kind of summarize the yoga, and I want to emphasize that it can work in both directions. So sort of a summary of the ideas that I'm trying to convey in this little section relating to principal G bundles. Summary, and this is what I would call topological, principal bundle theory. It's a sketch or a summary or a framework. And what that says is, if you've got F to E to B, remember that we can really, by definition, we've got a union of UI cross F modulo identifications, which are given by phi ij from UI intersect uj to some G. And so the idea is that we have around a structure group inside the homeomorphisms. Maybe it is all homeomorphisms, but usually, and for example, it can equal the automorphisms in some much more sort of interesting, enriched kind of category that than just spaces. So if F is Rn, yes, it's a topological space, but we can remember all the linear structure, in which case the automorphisms are no longer some infinite homeomorphism group or even an infinite diffeomorphism group. That's another example, is you can look at just all the smooth automorphisms. But even within those, much smaller are just the linear automorphisms, right? Once you have a linear structure on Rn. So our bundle then is made of these trivial bundles over UIs with these transition functions to relate the two trivializations. But what we can do is just take, we can replace F by G. And our phi ij for identifications are the same, and we replace maybe I wanted G to act on F on the right, and then we replace it by acting on itself on the right. And the point is that the same data allows us to define a principal G bundle. And so, so we have these sort of different approaches, and again, for characteristic classes of vector bundles, we found initially that thinking about that fiber as a Euclidean space and the geometry there was helpful in defining our characteristic classes. We haven't used as much the principal the principal ON bundle perspective, but it's there. We mentioned a little bit today that perspective explains another reason why why we must see symmetric polynomials come up. But in general, I like to go back and forth. There's a lot of, including current mathematics, where I feel like on the one hand, the right hand is sort of a bit more homotopy theoretic. And you often find yourself wanting to use a simplicial version of BG and things like that. Whereas over here, this can often be more geometric. But this passing back and forth is fairly rich, and sometimes you can even take questions in algebra or homotopy theory about classifying spaces for symmetric groups and find that some bundle theory or some other Schubert geometry helps you understand that. So the information flows in both ways, at least in my view. All right.